Good morning, everyone. My name is Andrea Ramirez. I'm a professor on low carbon systems and technologies in the Netherlands, and I'm very sorry not to be there, but I'm very happy that in these times, despite all the problems that we have had in the last 2 years, it is possible still to join you via just a video call. So I have been asked whether I wanted to reflect a bit on the message that is coming in the IPCC, but also that is coming in the media about the, what is the role of CCU for climate change. And what you can see, and is a little bit less present in the IPCC, but still you can read a bit on lines, is still a lot of conflicting message, I think, is still in literature about how much you need CCU to reach deep climate mitigation targets, and what will be the role, what will be the benefits, what are the bottlenecks. So we are still, the picture is getting clear, I think, as we move compared to 5 or 6 years ago, but it's still not completely and fully clear, which is normal because CCU is not one product, it's an umbrella of products. So there are many changes that need to be evaluated, and of course, not strange to have different answers. What we saw from the IPCC, of course, is right now, based on literature, they are forecasting a potential of 1 to 2 gigatons of CO2 a year as utilization potential, and they are saying, but it can go up to 20 gigatons by mid-century, based, and it's not in this line, but based actually on the availability of low carbon energy. What I have here as well are 2 different pictures of how we look at the contribution and the market and the role of CCU. In your left, you have an article that has been recently published by the Klein et al. On whether CCU contributes to the mitigation targets, which is actually a much conservative view on actually what is the contribution, and we are going to speak about permanence as and the system conditions that will need to be in place for those systems to actually contribute to a net zero economy. And in your right, you have a report from the Global CO2 Initiative. It's from 2016, but Volker is there, and he will give you a most updated report about the potential market. What I can tell you, and I think you see as well, is that there is a lot of messages, and we identify difference in the messages on which kind of product is actually being handled. So the carbon footprints will be quite different if you have a plastic, or if you have a cement product, or you have enhanced oil recovery, or you have a fuel. Where all the difference that we see that can explain the large ranges are difference in the way on the system boundaries. That means, what am I analyzing, what is inside my analysis and what is outside my analysis. Difference on how much low carbon energy is actually available and used in the process throughout the life cycle. So from the start until the end, on the end of life of the product. How do we treat the end of life emissions? Whether indirect effects are or not accounting on, what am I comparing my CCU technology to, and what kind of timelines I am considering. So I'm just going to go through some of these to try to explain why it's not a black and white picture. So I found this, and I just borrow it from the article from the Klein, because I think it provides at least a good way of looking at the scoping, among other things. But you depart from, things that we need to look at when we are assessing whether CO2 utilization can play a role on our net zero targets. Are, of course, what is the source of the CO2? How do I capture the CO2? And you need to be careful that some methodologies, for instance, mineralization, you can actually use direct atmospheric air, as you do with terrestrial biomass. In another case, you actually need more pure CO2, and therefore you need to extract the CO2 either from a point source, so the flue gas, which is more concentrated, or atmospherically, which is highly diluted. So CO2 is a problem in terms of climate change, but when you are going to try to use it, you still have the issue that is only 400 ppm level, which is factor of magnitude more diluted than when you have from a flue source. What are you going to utilize the CO2 for? What is the type of final product you are using? So what is the route? What is the product? What are you substituting? And what is the lifetime? So understanding the performance of CCU will require looking at the full value chain. And what we mean there is that system boundaries matter. And this is, I know it may be, I kind of designed this for an online presentation, so I don't know how big it is in your screen. But this was published in 2019 when we were looking at what negativity is, or what systems are carbon negative. And what we realize, of course, is within your system boundaries of a study, the study could be correct, but that doesn't mean that really you are avoiding or no emission. You have to take as broad a system boundary as possible. So what these kind of figures show you is just a steel production. It's a simple figure. So you have your factory, you put coal, you produce steel, and you have emissions. So it's around of 1 ton of CO2 for 1 ton of steel. So you can start doing things there. You can put carbon capture and storage. And in that case, your balance is going to be 0.1 tons of CO2 per ton of steel if you have geological storage and if you put your system boundaries around the factory. What we notice is that this number that is here, so you see here CO2 balance 1 ton positive per ton of steel, here 0.1 ton still positive per ton of steel. So only, for instance, can give negative if instead of coal, I will use charcoal, which is actually coming from biomass. And I take into account that the biomass has taken CO2, I have charcoal, then I have the plant, a steel plant, and a steel carbon capture and storage, and suddenly I got negative emissions. What is not in this picture are all the emissions of transport and charcoal production. So suddenly, if you have exactly the same system, but you began to account for all the intermediate steps, it goes again, the negativity decreases, and even if you account them for also the end of life, the negativity actually disappears. It's exactly the same system. We haven't changed any technology, we just have included or excluded elements of the analysis. So in order to really understand how carbon neutral or carbon negative is, you need to be very careful with the system boundaries that you include. And it looks like a very common sense conclusion, but when you try to compare life cycle assessments, then you realize that everyone is using different system boundaries, and therefore you can get even different conclusions for the same kind of product. This is just a life cycle assessment we did for use of CCS and CO2 in mineralization. We had case studies about actually using CO2 to having the concrete, so whether the concrete to absorb CO2 and actually is an utilization factor. But what we wanted to show just is you need to have the upstream emissions. You have to have, in this case, the cement and the concrete production. You have to take into account what happens during the use of the concrete, and you have to take into account what happens in the end of life. And only if you take all these flows that go out and in, then you are able to do a carbon balance and have a conclusion or insight of whether the system is going in the direction that you want to do. Now, how difficult could it be? You know, you do an inventory and you count carbon in, carbon out. So carbon accounting looks very simple. But what we have noticed is if you don't understand the life cycle concepts and the methodologies, then suddenly things begin to happen with the conclusions and with the analysis, which are not really proper, if you want to call it like that. And a typical confusion that we see now, and that is it's also a time of system concept, is the confusion between reductions and removals, which are for us from a life cycle assessment, and also from a climate science, two different things. Both are needed. So it's not like I'm saying you should only do reductions or you should actually only do removals. Actually, we should do both. And CCU can have a place in each of them. But we need to look at which part are we actually achieving with the CCU process. So what are we calling reduction? which sometimes people call carbon avoidance, it means that I'm still emitting. If you look in net terms, I'm still emitting CO2 into the atmosphere, only I'm emitting less than I would have emitted if I not have the CCU process or your energy efficiency process or any kind of mitigation process. So it's not that I'm not emitting anymore, it's just that I'm emitting less with respect to a reference. When we speak about carbon removal, we are speaking about a physical or reduction of CO2 from the atmosphere that is not coming back. And that's really a key difference. Where it comes, and it comes the confusion, is that sometimes when you do CO2 avoidance, you get a negative, a minus number in your calculation, and that is that minus sometimes is interpreted as a CO2 negativity, and I would like to say that's not the case. So let's assume that you have two products. You are going to produce a CO2 product that is going to replace a fossil-based one, or a bio-based plant, or another one. What you generally do is say, well, if I will have produced this product in the current way, fossil-based, for instance, I will produce X amount of emissions. But because now I'm not doing that, I'm producing in another way, for instance, a carbon neutral day, I avoid those emissions, I can take credit for that avoidance. So I am actually crediting emissions that will not happen because I avoid them. So the results of the CO2 avoidance is not an inventory of actual physical emissions, and that is where all the confusion happens. These are really important for our net zero, so we need to avoid CO2, but that should not be confused with actually the removal of the carbon negativity that we will need as well. Part of this, and when I say avoidance, is it depends on the product you are substituting. And that's also a little bit of the confusion. So let's say that you have a CO2-based fuel. You can use the CO2-based fuel to displace gasoline. That's what we want. We would like to displace a fossil-based fuel. But it could be that you displace instead biofuel, or you displace hydrogen, or you displace an electric vehicle. So you can understand that the amount of emissions that I save are different in the case of gasoline to the case of hydrogen or electric vehicle or biofuel. So it is really easy sometimes, and it's needed as well, but really easy to assume that you are going to be displacing gasoline. But if that is not the case, if the most likely competitor when you develop the technology may be other, you need to look beyond that. And it's in life cycle assessment, we are recommending to look beyond only one and to look at different scenarios to really understand what will be the potential impact of a CO2-based technology. This is also because a lot of the time we assume that displacement will happen. And a lot of life cycle assessment assume I'm displacing A with B, so one-to-one basis. If I was producing 1 ton of gasoline, of 1 ton, of ethylene, then I'm gonna produce instead of 1 ton fossil-based ethylene, 1 ton of CO2-based ethylene, which is just, a base chemical to produce plastic. But this is not always the case. Maybe I'm not displacing, maybe I'm just adding. So if I'm not displacing, if I keep producing the fossil base, and on top of that, I'm adding CO2 base, you will get, environmentally speaking, a completely different picture, most likely a negative picture, than if I really displace. And one question that is being discussed at the moment is, if we need displacement, what are the policy mechanisms? How are we actually going to monitor that we are displacing and not adding? The other things, two aspects that you need to take into account is the benefits of substitution will change over time. So if you are just substituting a system that is fossil-based, hopefully by 2040, a lot of the fossil-based will have now changed, and there the benefit of substitution decreases. That's normal, that's not a problem, that's actually where we want to go, but it needs to be taken into account. And the third point is that substitution is not inherently permanent. We have seen it with biofuels. So we need together to design mechanisms and think how the policies are implemented in a way that if the system shifts, that then you take out, for instance, a subsidy and the system doesn't go back to where it was before, because actually that will be not, I think, the more sustainable way to actually achieve the whole system. The fourth point, and I only have 5, so don't worry, I'm not going to go over, number 20, but the number 4 is I love the discussion about CO₂ utilization and negativity and neutrality are coming back to the issue of permanence. So removals are defined by the permanence. So how long do I need to take the CO₂ out of the atmosphere? That's temporal storage, taking the CO₂ away for 5 years or for 10 years or for 20 years. Would that be helpful? How long is long enough? And that is a discussion that is going back and forward. And of course, we know that there are products with a really short storage time. A typical one, for instance, urea. If you put urea in the soil, which is a fertilizer, the CO₂ will leave the soil within a week. But if you have a plastic in a car, or you have a steel, or you have a building, then the lifetime is much larger than weeks. So it depends on the product that you are speaking. And I love the discussion that we have seen here is around, can we then have circular economy? Having the products going more than one cycle, extending the life cycle. How can we account about that? Will that be helpful? And the main critical question maybe that we need to take into account is how then, if that is how we can permanence, how do we actually secure that that happens? And how do we monitor where the carbon is? Because you will need to keep custody of the carbon through the different cycles in order to actually claim benefits of circular economy. And what I put down is just a reference of the amount of, people, the fact that you can actually recycle something doesn't mean that it happens. And we have seen it with plastic, where only 9% of all plastic produced between 1950 and 2050 have been recycled accumulatively in history, and of this only 10%, so 10% of the 9% has been recycled more than once. So we need to do much better than these numbers if we are going to use this as an issue of permanent storage. On contrast, if you look at the steel, almost 100% is recycled. So it depends on the product that you are producing, but it's not as easy as just say circularity will solve it. And something that people need to understand, and I hope maybe you already know, is that there is no correlation between the time horizon and the atmospheric lifetime of CO₂. Because if you look at how long that CO₂ stays in the atmosphere, it is not one number. According to the IPCC, around 50% of the CO₂ is removed within a century, but there is around 20% that stays there for many millennia. So when we speak about global warming potential of 100%, that is not because that is the lifetime of CO₂. There has been an agreement among politicians and scientists to take that line. And you can see this when we look at the permanence of carbon in different kind of regulations. So you get UNFCCC and the past 2050, they say permanent carbon stored more than 100 years. If you look at the product environmental footprint, 300 years, international reference line, more than 10,000 years, life cycle assessment use 50, 100, 20 years, but the 100 years is the most common. But there is no one number. It's not scientifically 100, and that's it. On the question of whether there are benefits of temporal mitigation, so whether delaying the radioactive forcing of just putting CO₂ into the atmosphere, just having it there for 10 years or 15 years, that's not a life cycle assessment problem. We know how to count that. The problem is, I think, and that will be my point here, it is on how much you value short-term impacts versus long-term impacts. So if you have a really shorter time horizon, you decide that 20 years is long ago, you are valuing short-term impacts more than long-term impacts. If you do the longer the time horizon, the less value temporal storage has. And this is not an LCA problem, this is a value choice. And that's a discussion that needs to happen in that environment, for which a life cycle assessment then can provide a proper methodology to count. And my final message to you is, unfortunately, there is no one unique answer to the question of environmental performance of CCU. It is not that we can say it's always good and can say it's always bad. We do know, however, a couple of things. We know that the system boundaries matter. So therefore, the broader the system boundaries, the better to understand the impact. We know that the longer the CO2 is out of the atmosphere, the better. That without decreasing the importance of avoidance, we just know that if it can be longer, better. If you want to do impact in terms of climate change, the market size matter. The larger the market size, the more that can have an impact actually in our climate change targets. The source of the CO2 matters. So whether it's air, fossil, bio, geo, and that is not because the CO2 behaves differently in the atmosphere, that's not the case, but it matters in terms of whether we are or not closing cycles. The source and the amount of energy for the CO2 capture and the utilization process matters a lot. So we have seen again and again in life cycle assessment of CO2 utilization that where the electricity, the carbon footprint of the electricity, the carbon footprint of hydrogen, the carbon footprint of heat, how do I capture the CO2 determines in large part the footprint of the CO2 product. So no free lunches, we need really to understand where is that energy coming from in order to understand whether the CO2 utilization route is producing more or less emissions. And displacement is not a given. So we need to really try to understand, are we replacing, are we adding? What are we replacing? When are we replacing? And how are we monitoring that? If we just allow and think the market is gonna do that and we don't need to take care of it, we are in high risk of actually going into adding instead of replacing over the short term at least. And that will be against what we are actually trying to do, that is move toward hopefully a less CO2 intensive economy. And that is it.